Hello everyone, it is my great pleasure to present our paper in Ubiquitous. I'm from the University of Electronic Science and Technology of China. The topic of our paper is towards cross-domain CSI action recognition through one-shot bimodal domain adaptation. I will first introduce the motivation of our work, then the objective we try to achieve. After that, I will explain our method in details, and then present the evaluations on activity and gesture recognition. Finally, draw the conclusions. Over the past years, there have been many studies on Wi-Fi sensing, ranging from localization, action recognition, to vital sign monitoring. Most of them make use of channel state information called CSI in Wi-Fi to achieve sensing. Among them, action recognition is one of the most useful applications. Most CSI action recognition solutions exploit supervised learning to achieve high accuracy, requiring the training data and the testing data to follow the same distribution. This indicates that CSI action recognition under supervised learning only works well in steady environments. If the environment changes, for example, user change, location change, or room change, the recognition accuracy will decline dramatically. To keep high performance in a new environment, a large number of new samples need to be collected to retrain or fine-tune the original model. This is impractical. To minimize the effort of domain adaptation and meanwhile keep high accuracy, we propose a one-shot bimodal domain adaptation method, aiming to achieve cross-domain action recognition. Utilizing the source domain data and one sample per action in the target domain, our method generates a large number of virtual samples for the target domain. Virtual data generation is through linear transformation and synthesis autoencoder. To further enhance the accuracy, our method fuses the amplitude and the phase under the criterion of consistency by fusion autoencoder. The fused features of all the virtual samples are used to train the action classifier for the target domain. Our method is composed of data collection, preprocessing, virtual data synthesis, bimodal fusion, and action recognition. The key components are virtual data synthesis and bimodal fusion. As there is only one sample per action in the target domain, the data synthesis component generates a large number of virtual samples for the target domain through linear transformation and synthesis autoencoder. The bimodal fusion component extracts the consistent features from the amplitude and the phase by cosine similarity via fusion autoencoder and concatenates the consistent features for the subsequent action classification. Before virtual data synthesis, the amplitude and the phase are retrieved from CSI, undergoing noise reduction in amplitude and shift removal in phase. After bimodal fusion, the fused features of the virtual samples are used to train the action classifier and recognize the actions in the target domain. The amplitude and the phase retrieved from the raw CSI cannot be used directly for action recognition, as the amplitude contains noise and the phase contains random shifts. The data preprocessing goes through amplitude denoising, phase sanitization, segmentation, and resampling. The raw amplitude sequences are denoised by a Madden filter. The raw phase sequences are sanitized by a linear transformation method. The denoised and sanitized data are segmented to retrieve the action part by mean square deviations. Finally, the data are resampled to keep a consistent length by interval sampling. Target domain. The target domain has only one sample per class. It is too few to train a classifier. So, to achieve cross-domain action recognition, we augment the dataset of the target domain. We generate virtual samples for the target domain, using the real samples in the source domains, and one sample per action in the target domain. As the virtual data are for the target domain, they should contain both the action information and the target environment information. The action information mainly comes from the source domains, and the target environment information comes from the target domain. Taking a sample from the source domains and a sample from the target domain, we apply linear transformation on them to generate the virtual sample. Alpha and beta are the domain weights to balance the importance of the domains. Because different domains have different environmental characteristics, we set the domain weights adaptively by applying synthesis autoencoder on the virtual samples to determine their values. In addition to the domain weights, the synthesis autoencoder tries to make the virtual data close to the target domain data by minimizing the distance between the synthesized virtual data and the target domain data. The red curves in the two figures show the virtual amplitude and the virtual phase. They are similar to the real target domain samples, thus can be used to train the model for the target domain. From CSI, we can extract amplitude and phase. The two models are affected by the actions simultaneously. Hence, they have consistency. We fuse the two models in the feature level under the criterion of consistency. The fusion autoencoder is first applied on the amplitude and the phase to extract their own action features, then leverages cosine similarity to measure the consistency and minimize it. That is, to minimize L cos. In addition to minimizing the distance between the amplitude and the phase, the extracted features should keep the original features of each model. Hence, the reconstructions of the amplitude and the phase should be as similar to the original as possible. That is, to minimize LMSE of the amplitude and the phase. The total loss of the fusion autoencoder can thus be defined as the summary of L cos and LMSE of the amplitude and the phase. The extracted features of the amplitude and the phase are concatenated as the fused features for action classification. We employ CNN as the action classifier, which contains 3 convolutional blocks followed by 3 fully collected layers. To evaluate the proposed method, we conducted experiments on activity and gesture recognition. We deployed 2 laptops equipped with Inter-Wi-Fi Link 5300 as the transceivers, each having 3 antennas. After data preprocessing, each action sample had a time sequence of 200 packets with 270 dimensions. We set up 2 scenarios for activity recognition, a lab and a lobby. The volunteer performed 4 activities at 8 locations in the lab and 5 locations in the lobby, and each activity was repeated 20 times. In the lab, 7 locations were taken as the source domains and the left one as the target domain. In the lobby, 4 locations were taken as the source domains and the left one as the target domain. We used the source domains and 1 sample per activity in the target domain to train the adaptation model and tested on the target domain. The method was evaluated at all the locations in the lab and the lobby, with each location as the target domain in turn. The average accuracy reached 85% in the lab and 90% in the lobby. We also collected data for gesture recognition in 2 scenarios, a lab and a lounge. 6 volunteers performed 6 gestures in both scenarios. The gestures were common letters L, O, V, W, Z, S. Each was repeated 20 times per person. For gesture recognition in the lab and the lounge, we took 5 users as the source domains and the left one as the target domain. We used the source domains and 1 sample per gesture in the target domain to train the adaptation model and test it on the target domain. The method was evaluated on all the users, with each user as the target domain in turn. The average accuracy achieved 91%, 91% in the lab and 85% in the lounge. For activity recognition across rooms, we took the lab as the source and the lobby as the target and vice versa. The experiments were conducted at each location in the target room in turn. The average accuracy achieved 87% from the lab to the lobby and 82% from the lobby to the lab. For gesture recognition across rooms, we used the lab as the source and the lounge as the target and vice versa. The experiments were conducted on each user in the target room in turn. The average accuracy achieved 83% from the lab to the lounge and 88% from the lounge to the lab. We compared our method with the existing works. We compared with the data augmentation method in FIDO, which leveraged variational autoencoder to synthesize virtual samples from the labeled samples. We compared with CSI GAN, which leveraged semi-supervised GAN for CSI-based activity recognition using unlabeled samples to generate virtual samples to train a robust discriminator. We also compared with no adaptation and fine-tuning. Using the same activity datasets and gesture datasets across locations and across users as well as across rooms in multiple scenarios, our method achieved the best performance in the target domains. For ablation study, we apply linear transformation to synthesize virtual data and set the domain weights adaptively through synthesis autoencoder. To verify its effect, we compared it with fixed domain weights. The results show that dynamic domain weights outperformed fixed domain weights. We leverage synthesis autoencoder to reconstruct the virtual data and make them close to target domain. To verify its effect, we compared it with not using synthesis autoencoder. The results show that the synthesis autoencoder improved its accuracy. The fusion autoencoder extracts the consistent features from different but consistent models and meanwhile keeps their original features. To verify its effect, we compared it with not using fusion autoencoder. The results show that the fusion autoencoder improved the accuracy. To evaluate the impact of the number of source domains, we tested on different numbers of source domains with one target domain. The results show that more source domains led to better performance. We evaluated the impact of the number of samples per action in the source domains. The results show that the accuracy increased with the number of samples in the source domains. We also evaluated the impact of the number of samples per action in the target domain. The results show that more samples achieved higher accuracy, but they all incur higher cost. To conclude, To achieve cross-domain CSI action recognition, we propose a one-shot domain adaptation method based on virtual data synthesis and bimodal fusion. The method generates the virtual data for the target domains by linear transformation and synthesis autoencoder, which sets the domain width adaptively and makes the virtual data close to target domain. The method fuses the amplitude and the phase by fusion autoencoder, which extracts their action features and keeps their consistency to the same actions. Evaluations of activity and gesture recognition in multiple scenarios achieved acceptable accuracy across locations, users, and rooms. The limitation of the method is that it still requires one sample per action in the target domain. So zero-shot domain adaptation is our next work. Thank you. Any questions?